It's my great pleasure to introduce our next speaker, Dr. Rebeca Santamaria-Fernandez. Rebeca's first degree was obtained in Spain, and she subsequently did Masters and PhD degree in the UK, a postdoctoral time in France, before she spent time at the laboratory as a government chemist in the UK, and that's where I first came to be aware of Rebeca's work. She's now returned back to Spain. Rebeca has considerable experience with ICP-MS, AES, isotope ratio mass spectrometry, and multi-collector ICP-MS, which she'll be talking to us about today. It's not just the quality of Rebeca's work that I think is impressive, but to me it was the depth and the breadth of topics that she's covered in such a short period of time.
Thank you so much, Archie, for the kind introduction. I'll pay you later. So, good morning, everyone. Just a brief overview of what's been happening. You can see on the early 80s, the first ICP-MS became commercially available. Since then, a whole bunch of things have happened in a very short space of time. The first multi-collector ICP-MS appeared in the early 90s, and the first publications were very much focused on cosmochemistry and geochemistry. We then started to have a few more analytical publications, and within those, we started looking at stable isotope ratios, and that's where my work is focused for the past 5 years. So I'll touch on those very briefly, and then I'll go to one of the newest developments, which was carbon isotope ratio by multi-collector ICP-MS. Talk about the present, so when I'm saying present, I really mean the past couple of years and the next year or so. And then, as I say, go to my futuristic view of what's going to happen. So for those of you who don't know, ICP-MS was born in the 80s. It's a multi-elemental analysis technique. It really has great sensitivity as opposed to some of the classical techniques that we used before then. And it's quick, so it really has both of those. The plasma is the ionization source, so you all know, I guess, what an inductively coupled plasma source is. It really is just a fireball that is ionizing your sample. It then goes to the mass analyzer, which is your detector that basically measures the mass of those ions. It can go down to really low levels, down to DPT in some cases, not all of them. And you can either do qualitative analysis, quantitative analysis, and in the best case scenario, measure isotopic ratios. So those are the most common well-known mass analyzers. Either a sector field, where we basically distinguish ions because of their energy, and the mass, or quadrupole, measures mass charge ratios. Those have a drawback, and what happens is that we call those scanning ICP-MS. They basically measure one mass or another. So when you're looking at several elements, or several isotopes from the same element, you have to be jumping from one mass to another. So that's the scanning ICP-MS. So there's obviously a need of an instrument that could do both masses at one time, which is why the multi-collector ICP-MS came into the picture. So it appeared in the early 90s, the first paper that was published in JAAS, funnily enough. You can see a very modern cover of JAAS in grey and pink at the time. And I like this translation because you're going to see how the journal has changed throughout the times, as we all have, unfortunately for some. So this is the first ICP-MS that was coupled to a 7 Faraday detectors, which meant that you could look at up to 7 masses at any one time, opening a whole range of possibilities to measure isotope ratios. This paper in particular was focused on uranium and lead isotopic ratios, which is what happened for the first few years of existence of multi-collector ICP-MS. Most work was published on uranium, lead, hafnium, etc. So my friend Chuck here, who some of you guys know, Chuck works in the UK, in the USA for Thermo Fisher, and has done a fantastic review up to 2007 of what's been published so far using multi-collector ICP-MS. So you can see here the first few years, it really was just a few papers, and when I say a few, it really is, you can count them with your fingers. So it was 4 papers, 5 papers, it was a very novel technology, and people were seeing how far they could go. And they really focus on lead, uranium, hafnium, so mostly cosmochemistry and geochemical applications. It then had a bit of a boom a decade later, and you can see how it grew exponentially up to 2007, which is where this review ended. And it was only in 2006 when the first paper looking at sulfur, so stable light isotope ratios of sulfur, were analyzed for the first time using a multiple lecture ICP-MS. Once again, it was a cosmochemistry, geochemistry application, but nevertheless, the first time that sulfur was mentioned. So what I've done is I looked at the past 3 years that Chad missed out on this review that was published in 2007, and you can see there's been a massive change. I mean, it really is a blooming field where publications are growing exponentially, and God knows where we're going to go in 2012. There's now been more than 4,000 publications involving multiple lecture ICP-MS. And although it's still very much geochemical and cosmochemical applications, there are now new fields like forensics and biochemistry, archaeology, that now have realized that there is an instrument that can help them in those fields. So I really foresee police laboratories and food analysts buying multiple lectures ICP-MS in the near future, because it really can help them. So since 2006, when this first sulfur paper appeared, we have been working at LGC in the UK in a few method developments and applications of this technology. We've also looked at carbon isotope ratios, and we've added another element to the periodic table that the multiple lecture can now cover. And I'll briefly review all of this and tell you a bit about each application. First of all, let me introduce my best friend for the past 5 years, the Neptune. My mum really thought this was a person, so I kept talking about the Neptune this, the Neptune that, and she was like, who is that Neptune? So the Neptune is a multi-collector ICP-MS manufactured by Thermo Fisher Scientific. It's an ICP-MS with a particularity that it does have a collector array, so it does have 9 Faraday collectors, as well as an SEM that increases the dynamic range right in the middle, so you can see it right there. And you can choose to use either the SEM or the actual Faraday. It also has some ion counters that work down to PPT levels, but those have a massive drift with time, so they really are to be used in short time applications. So this is it. This is the Neptune. This is my colleague Peter here, so you can see the size of it. That was also really scary the first time I went to LGC and saw the instrument. I was like, am I really going to work with that thing? Is it that big? Then you realize that half of it is empty in the inside because it needs some ventilation, so that's fine. It's not as big as it looks. So the precision in a worst case scenario is up to 0.02%, and that's the worst you can get on a bad day. It has high resolution and medium resolution options, and it has dispersion lenses, and all these combined make the possibility of measuring interference-free cycles possible, basically. Measuring isotope ratios is then easy with this kind of instrument. Not as easy as one would say for some of the elements, but we can now do what the ICP-MS couldn't do before. We can measure different masses at one time. So let's touch on the sulfur applications. You all know sulfur is in a wide variety of materials, and the isotope ratios do change, mainly due to fractionation processes, bacterial action. So sulfur is bound to be in things, but it's also bound to have a different isotopic composition. And these can tell us a lot about where that wine comes from, or where a person has been, etc., etc. So this is why we are interested in measuring those sulfur isotopic variations. Conventionally, geochemists and geologists have been measuring sulfur variations, but not using ICP-MS. They've been using gas source isotope ratio mass spectrometry, where the sample has to be combusted to SO2 or converted to SF6, which is tedious and complex and a long process. So the ICP-MS is a quick alternative to this, as well as they need to do an upstream correction because they are converting the sample to SO2. So the ICP-MS really is a quick alternative to this. And we've applied it to several samples, and I'll go through those now. So if you remember when I showed you the 9 collectors here and the SEM there, basically this is the configuration that we use for sulfur ratios. So we have sulfur 32 that will go into the central Faraday cap, and sulfur 34 that will go into the 4th high cap. We then have to jump, unfortunately, to measure 28 and 30 silicon. And you're probably thinking now, why is she talking about silicon? Nobody's talking about silicon here. Well, we have to, because one drawback, I guess, that we have is the fact that heavy ions don't behave the same as the light ones. So we need to use a similar pair of isotopes to correct for these effects, for the mass bias effects. So if we use 28 and 30 and think that they'll behave similarly to 32 and 34, we can then correct for that effect. So this is what you see. no pre-picks in here. What you see is a pick with 3 bellies, because we know that sulfur has an interference from oxygen, and thanks to the medium resolution mode, we can now distinguish that sulfur peak from the sulfur plus oxygen from the oxygen interference on itself. So this is going to be our interference-free measurement area. And exactly the same thing happens with silicon. So we're now peak jumping from 3195, where our magnet is set, to 2896, where silicon will be measured. We'll be doing this, and we'll be having isotope ratios for sulfur and for silicon that we then use to correct the sulfur ratios. So at first, we knew there was that paper, and we knew it was a geological application, but we wanted to do a very thorough review meteorologically, because that's what LGC does, metrology, so we had to do some metrology here. I mean, we are analytical chemists. We want to know the error, we want to know the number, we want to know how sure we can be that the number we're giving anybody is right. Geochemists look at the differences, and in some cases the differences are so big that the error doesn't really matter. In our case, it does. So before we went any further with the methodology, we had to try different standards and see how those corrections worked, and do a systematic comparison to be able to say what works best and what's the expected error. If we're expecting police officer or food analyst labs to use this technology, we really have to tell them what the error is going to be for that technique. Otherwise, they'll just take it for granted and think that 5 is just 5 ppm, and it's never going to be the case in science. So we did a thorough and systematic comparison of the 2 standards, and you do see that there are some differences. So if an isotope ratio mass spectrometry lab measures some samples using a standard or another one, the relative number that they get in the end, yes, it is comparable, but it's never the same. And because they don't tend to calculate uncertainties, that leads to a problem sometimes. So we did do a comparison between silicon correction and bracketing and proved that the uncertainties are. So we now go to one of the applications. We remember a few years back then, we had a meeting with some pharmaceutical companies, and you all know how counterfeit pharmaceutical drugs are in the market. Unfortunately, they are. And over 50% of the counterfeit cases come from internet. However, there are cases in shops as well. So this is something that worries pharmaceutical companies a lot. And there is not such a technology yet that can work every time and that they can take to court and it will go through as evidence. So we used this method because we knew it could provide reliable numbers to detect counterfeit pharmaceutical drugs. We basically got a set of drugs from a major pharmaceutical company in the UK and looked at those for sulfur isotope ratios with the Neptune and for carbon isotope ratios using conventional IRMS. So as you can see here, out of the 360 drugs, 3 duplicates of each, the genuine ones cluster together very well, whereas the counterfeits also cluster together in a different place. So we can now tell with confidence that those drugs are fake, and this could hold in court as evidence. The method has been validated, and we can now say that these drugs are not real. So this is just an application where there was no technology before that could do such a thing. There's many classical methods that could tell you yes or no, but quantitatively speaking, we can now tell that these drugs are fake. What we did after this is to make sure that the genuine tablet had a genuine signature, isotopic signature. We then looked at different approaches for sample introduction. So we looked at the tablets as such, just diluted in some nitric acid. We then did some laser ablation. This is the quick one and the one that the pharmaceutical companies liked, because that meant they could bring in some tablets from Heathrow Airport and we could quickly compare them to the genuine ones and see if they were real or not. And to make sure that we were looking at the right thing, so at the API, the active ingredient in the tablets, we then did some HPLC analysis so that we could separate the active ingredients and characterize that for isotope ratios. And you can see that the same genuine tablet leads to the same isotopic signature in the 3 cases. The uncertainty was evaluated in each case, and again, although the uncertainties are slightly bigger when you introduce new things to the ICP-MS, they are comparable. So this was published in JAAS. So other applications that we've been working on are beer analysis for food authenticity or drinks authenticity and location. Colleagues of mine at LGC have been working on bottled waters as well to see if they could distinguish the origin of the waters. And we've also been working on characterization of some spikes to then be used for isotopic dilution.